So let's talk about detecting radiation. And I'll bring one of these to class, so you'll probably have already seen it by the time you watch this video. But here is a cylinder. And, well, let's draw it this way. I'll draw it like the one that I have. Here is a metal cup. And it's, a thick metal cup. And inside that metal cup, there's a little insulator here on the bottom, little through-hole fitting. And coming up through there is a wire. And this is hooked up to a screen. And on the top of this thing, you have a thin, paper-thin mica window. And inside this chamber, you have a gas like argon, an inert gas, and it's at low pressure, and it's kind of sucking that mica window down. And what you do is you put high voltage, typically several thousand volts, between the screen and the chamber. So now what you have is, and let's see, did I do that right? Let me see if I might have this battery put backwards here. We want electrons to go that way. Yeah, let's do it the other way. Okay, so here's our high voltage. And so let's say you have a bit of radioactive stuff here. Say it's the americium, I'm not sure if I'm saying it right, but the stuff that's in your, americium. I can never pronounce this one right. But it's element 95, and they're used in smoke detectors. And so if you take an older smoke detector apart, it has this little piece of radioactive stuff, and it's making these, I think it's a beta emitter, but I'm not sure. Pretty sure it's a beta. And so here's your beta particles kind of coming out from this thing. When one of them passes through this mica window, it has the chance of interacting with an argon atom, and specifically interacting with the electrons on the argon atom, and causes an electron to get knocked free. So now you have a free electron there. Now, because of the high voltage, you have a very strong force on that argon atom. Because remember, this whole plate has become negative now. And this plate here is positive. So that electron starts moving through the gas. But on its way, it interacts with other electrons and knocks them off of their atoms and other electrons. And you get an avalanche of electrons that hit the cup and cause a sudden change in the charge on the cup, which can be detected. Here's a detector. And the detector will make a click every time a beta particle or alpha particle or gamma particle has interacted with a single argon atom. And so you'll get these clicks coming out of it, and you can literally count how many particles enter through the mica window. And so if you listen to a Geiger counter, it sounds such as this, like. I wasn't just clearing my throat, I was trying to imitate a Geiger counter. It makes all these clicks. And so you count particles. And that's how a Geiger counter works. And you can do a lot of interesting experiments. Say you have your radioactive stuff, And you want to find out, and say it's a gamma emitter. So say you've got some gamma particles, okay? And you want to find out how energetic they are. Well, you can put lead sheets of different thicknesses there, and if it'll make it through, say, 2 millimeters of lead, you can estimate the, or say when you get to 2 millimeters of lead, you've stopped half the particles. Or, well, it doesn't work quite that way. Say you got 2 millimeters of lead, and when you got that thick, it finally stopped letting particles through. Well, then you know the energy of your gamma particle, and you can estimate it. So that's, Geiger counters are a good way to detect radiation. I have one. I'll bring it to class. So now let's look at nuclear energy and how it's produced. As we said previously, there are two different types of nuclear energy. There is fusion and there is fission. And these are two separate processes. Fission is when you take a heavy element, such as uranium, and there's lots of different isotopes of uranium. So let's see which one they talk about in the book. So one common one is uranium-235. So uranium, let's see here. I'm looking it up on my periodic table. And I'm not running into it. Hold on. Okay, uranium is 92. So you've got U92, 135. So you can calculate the number of protons and neutrons. So here's that uranium nuclei with its protons and neutrons, and it's unstable. And I think we need to talk about something called half-life, first of all, before we can really get to the nuclear energy. So sorry, I forgot about that. Let's talk about half-life real quick. So the different isotopes in a material they live for different amounts of time. So, for example, phosphorus. Let's do this example. We'll come back to this fission and fusion in a minute. Say you have phosphorus 32, and it said phosphorus 32 has a half-life of 14 days. So what that means is, let's look at the decay chain for phosphorus 32. So phosphorus 32 turns into sulfur 32, and it does it by beta emission. So okay, I guess I just write it over here. Okay, so that's the decay chain. Now, it's got a half-life of 14 days. So the book talks about this, but I'll go over it. If you start off with 16 grams of phosphorus 32, in 14 days, you'll have 8 grams of sulfur 32 and 8 grams of phosphorus 32 left. You wait another 8 days, then you'll have only 4 grams of P32 and 12 grams of sulfur 32. You wait another, so here's 14 days, here's 14 days, so you wait another 14 days, and now what you're left with is 2 grams of P32 and 14 grams of sulfur 32. So this is what's called an exponential decay curve. Looks like this. So here is your time, and here is your amount of material. So here's 100%, what you start with, and it decays, but it's asymptotic to the x-axis, so it never really gets to 0. So there's always a little bit left, no matter how short the half-life is, except for the fact that it's the number of atoms is a definite number. So when you have one atom left, if its half-life is 14 days, there's a 50% chance that in 14 days that single atom will have decayed, and when the last atom of the radioactive stuff is gone, then indeed it's done. So you're probably wondering, why does it do this? Why does it randomly decide to decay after a certain amount of time? This is a weird quantum mechanical thing, and I'm not going to explain it now. So just know that every isotope has a half-life, and when the time of the half-life is up, half of the amount of the original isotope is left over. Okay, let's do our last talk on nuclear energy and pick it up in the next video.